Hello, this is Professor Neshaba, and I'm here to help you out with the computational guided inquiry for Gen Chem delocalization and chemical structure. And the first part I want to just talk about here is the Prelab. So these are the first molecules to look at. It's nitrogen dioxide and ozone, and these are the things that I want you to put together in your lab notebook for this. So I don't have pictures of NO2 to show you in this video, but I do have pictures of ozone to show you, and NO2 is quite similar. So if you skip up to figure 1 in the handout, here you can see the resonance forms of ozone, and so these are the two equivalent resonance forms put together using the XYZ method. As you can see, these are the lone pairs that will form a double bond right there, and so on. So those are the two equivalent resonance forms. How many pi bonds do we have? Well, there's just one pi bond because the other one is a sigma bond, and we have 2 electrons in that pi bond. So that's the first couple things to do. Bond orders. How are we going to do that? Well, on average, it looks like we have, we've got 2 bonds there, 1 bond there, and here it switches to 1 and 2. That means on average we have 1.5 bonds, so the bond order between those two oxygens is 1.5. And finally, what about the orbital hybridization on the central oxygen? Well, to do that, we're going to use our device whereby we calculate the steric number and use that to deduce the orbital hybridization. And you can see that the steric number on that central oxygen is 3, 1, 2, 3, and that means this must be an sp2 orbital hybrid. And if it's sp2, that means that the angles must be 120 degrees or so, and so this is not depicted in that geometrical way. It would obviously be bent. Ozone is bent molecule. All right, the next set of questions on the Prelab have to do with XYZ delocalization on the CH3COCH2 minus anion. So here I've drawn for you 2 of those, the resonance forms. These are the 2 most important ones. And how many pi bonds and pi electrons are there? Well, there's just 1 pi bond with 2 electrons, and there they are again. So at any given time, we just have 1 pi bond. Let's see, how are we going to decide on the orbital hybridization of the carbons? Well, this is a CH3. Its steric number is 4. Therefore, this must have tetrahedral angles around it, 109, and it's an sp3 hybrid. This carbon here has got 3 things around it. Doesn't really matter which one of these we look at for that. It's still got 3. Steric number of 3 means sp2 orbital hybridization and 120 degrees all around. Fine. And then this carbon, this is the carbon where it makes a difference whether we're looking at one resonance form or the other. We can go to this first, the A structure. The number of blobs around that carbon are 1, 2 for the hydrogens, 3 for the lone pair, and 4 to that next carbon. So if it has a steric number of 4, that means it must be sp3 orbital hybrid, and the angles associated with those bonds would be 109, the tetrahedral angle. If we go over here and look at this resonance form, now the steric number is 3, 2 for the hydrogens and 1 for that double bond, sp2 orbital hybridization, and angles of 120 degrees around there. So one of the goals of this whole laboratory experiment or computational experiment is to see which one of these actually happens in the molecule. Does it look like it's 120 degrees, or does it look like it's 109 degrees? And that will actually tell us what the orbital hybridization is, and therefore which one of these resonance structures is predominant. Let's see. There's a couple more. The next two I've mentioned are ethene and ethine, and I'll just go to you can go to the Wikipedia site for that. Here's a depiction of ethene, which as you know is the other name for it is ethylene, and so there's a picture of that one, and for ethine, also known as acetylene, there's the picture for it, well, the angles are all 180 degrees there. And let's see, the last three that I'm asking you to put together as part of your pre-lab are resonance forms, or rather just Lewis structures for these three molecules here. So this is the allyl cation, and there's its structure. It's a cation, it's got a plus charge on it there. That's why this doesn't have a complete octet. Here's butadiene, okay, and here's 1,3,5 hexatriene, and so there you go. And so those are the that's pretty much the whole pre-lab. Let's see, what else did I ask you to do on these? Well, there's the Lewis structures on those that I just mentioned, total number of pi bonds and pi electrons, and orbital hybridization and bond angles. Well, let me just take you through one of those. For butadiene, I'm looking at one. There's a pi bond. There's another pi bond. So there are 2 pi bonds. That means 4 pi electrons. And steric number on this carbon is 3, so that must be sp2. That must be sp2 for the same reason. sp2, sp3, sp2. So that's sp2 all across the board. And you can use the same logic to figure out what the orbital hybridization is on all those carbons, and it's looking to me like it's sp2 all across the board.